Section 4.5, quantitative chemical analysis. So here's the last section in chapter 4, this monster chapter here. Quantitative. So that word quantitative means quantity. In other words, looking at actual numbers, measuring them, quantity. As opposed to qualitative analysis, where you're just trying to look at the identity. You're just trying to identify, hey, what did I get? What's the identity of it? I'm not so much worried about percent yields or anything like that. Okay. So 4.5, we are trying to look at quantitative analysis, so taking careful measurements of exactly how much. The book goes through two main, there's actually three, but two main types of quantitative analysis. The first one, titration. Now we've actually definitely doing titrations in the lab here. Quick definitions on titration. You're trying to analyze something, usually it's in this beaker. See this picture here from your book? Down there, that's what I'm trying to analyze, and therefore they call it the analyte. That's what I'm trying to analyze, figure out how much is in there, how many moles are in there, or what's its concentration, that kind of a thing. I'm doing that by doing a reaction. In this case, whatever is up here in my burette, my tall skinny thing with the valve on the bottom here, they call that the titrant, because I'm titrating, that is to say adding drop, drop a little bit, recognizing I can measure exactly how much I add by looking at the scale here, and I add it until I reach the end point of my titration. My end point is where I've added exactly the same number of moles of titrant as I had analyte present down here to begin with, the end point. Alright, or at least a stoichiometric number of moles, if it's not quite a one-to-one. Indicator bottle, I guess that's what this is down here. We add a couple drops of that so it does a nice color change at the end point so we can know when to stop adding my titrant. Right? And finally, you've got to measure the quantity that you've added, the change in volume. Right? And I'm just going to put this up here to remind you. Here's a blow up of the burette scale at the very top here. Here's a blow up, and actually I'm going to blow it up even more so we can really take a look at this. Here it is. And so this is in milliliters. And this big line here would be 0 milliliters. Here's 1 milliliter. 2 milliliters is down here, right? And here's my meniscus, my smiley face of my liquid. And remember, you always want to look at the very, very bottom of that. And so, wow, if I really blew this up here, here's my meniscus. You see it's like this little black, you got this dark area, then this light area, and the very bottom of that meniscus is that little thin black line right at the very bottom here. So how would I actually read that? Well, here's the 0 milliliter mark. Here's the 1 milliliter. It's definitely somewhere between 0 and 1, that's for sure. But then they've got further gradations, and 1, 2, 3, 4, 5, 6, 7, 8, 9. Apparently, there's 10 divisions here, so those are tenths. So this is 0, this one would be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, etc., etc. My meniscus is coming up definitely somewhere between 0.3, 0.3, and right here 0.4. So if I'm going to read this, remember, significant figures, you read what you know for sure, and then you add one more digit where you have to guess a little bit. You have to approximate. And so I know for sure it's at least 0.3. I know for sure it's not quite 0.4, right? So it's somewhere between that. And so if I'm writing this, I'm going to write for sure with certain 0.3. And then I can add one more digit where I'm approximating it a little bit. And I look carefully here, that bottom one, to me it looks like it's, well, it's a little more than halfway between this line, the 0.3 line, and then the 0.4 line, you know, right there. And so I'm going to call that 0.6, a little more than halfway. And so the correct way I would read that burette is 0.36 milliliters. Alright, so make sure you read them correctly and get the right number of significant figures. Alright, so again, at the end point, which is also called the equivalence point. There's a slight difference there. I'll talk about it in just a second. The moles of the titrant equals the moles of the analyte. We've reached them, so there's not a limiting reactant, in other words. There's not an excess of one or the other. We've added enough, so it's exactly 1 to 1. It's exactly correct amount that we've added. Okay, so in that case, again, moles of titrant equals the moles of the analyte. All right? Now, again, technically that's called the equivalence point because we have an equivalent amount of titrant and analyte. So why do we use the word endpoint? The endpoint technically is the place where the color changes due to that indicator that we put in. So it goes from clear to pink, or it goes, you know, from yellow to pink, or whatever it might be. It goes from yellow to purple, right? Something like that. Where you see the color change, that's called the endpoint. Now, hopefully, that change is at exactly the same as the equivalence point. We want it to change right when we've added the same amount of moles of titrant as we had analyte. So a good indicator, if we choose properly, a good indicator will have or show its endpoint at exactly the same place as the equivalent point. Right. Now, that's not always exactly true. Certainly some indicators are better than others. Some indicators have soft endpoints where it's kind of hard to tell, am I there? Is the color change or not? Where other ones are very crisp. So, yeah, there's a lot that falls back on that indicator. But for the most part, hey, we do the best we can. We choose the indicator, and then we just have to assume, yep, that it's showing me the correct equivalence point as well. Now, another note I'm going to make about this, technically the equivalence point is not necessarily where the moles of titrant equals the moles of analyte. It's where we've added enough titrant to completely react with the analyte. What's the difference? Well, sometimes in my balanced equation, it might not be a 1-to-1. Those coefficients might be a 2 and a 1, or a 3 and a 5, or whatever. Right? What we want is for them to totally and completely react with each other. Right? Which usually comes back to the idea that the moles of one equals the moles of the other if it's about a 1-to-1. But just be warned, it's not always necessarily. All right. So obviously we are analyzing this analyte down here in a very quantitative way by adding something that we know how many moles, we know the volume, and we should be able to do a calculation now to figure out how much of the analyte was actually present. So, all right, example 414. 414 asks, here's a picture of the guy titrating and adding that. That's funny. By the way, I'm glad he's got goggles on, but what is he doing wrong here? He's pouring that in at above eye level. Never do that. Always hold it below eye level when you fill it, right? That way it doesn't have nearly as likelihood of splashing you, hitting you in the face, whether you got goggles on or not, right? But always have goggles on, of course. Okay, going back to 414, let's see. It says the endpoint of a titration of 50.00 milliliters of aqueous hydrochloric acid was reached by adding 35.23 milliliters of 0.250 molar sodium hydroxide. All right, so analyte, we have 50 milliliters of HCl. We don't know its concentration, so we don't know how many moles are there, but we know the volume. It was 50 milliliters. It's in the beaker in the bottom there, and it's HCl. So we're describing down there the analyte. We got 50 milliliters of HCl. And then we titrate it, and it takes 35.23 milliliters of 0.25 molar sodium hydroxide. So that's what's up here, right? That's on the top here. That's my titrant. Now I know the titrant very well. I know its exact concentration, 0.250 molar, because I probably made it up myself. I weighed it out and made it exactly what I needed it to be. And I know exactly how many milliliters it took, 35.23 milliliters. It says, hey, what's the molarity of that HCl? So here, I'm trying to figure out about this hydrochloric acid down here. I know the volume, that's it. I'm trying to figure out how much is there as far as what's its concentration. Is it really concentrated or is it dilute, right? What is that number? That's what they're asking me to calculate. Okay. Here's the picture. I like to draw it out to keep my mind straight as to what is in where. HCl is in the bottom, 50 milliliters. Sodium hydroxide is 0.250 molar, and I know I added 35.23 milliliters. All right. I should be able to do a stoichiometric type of a calculation here using my balanced equation to figure this out. Here is my balanced equation. Everything turns out to be a 1 in this one. That'll make it easier, but hey, if it doesn't, no big deal. Just use whatever the balanced equation shows you. All right. What do I know? I know the volume of this, but I don't know its concentration. That's what I'm trying to figure out, actually. I know everything about the sodium hydroxide, right? And the quantity, that's what I'm after, the quantity of the HCl as far as its concentration. Right? So I want to start with the quantity of what I do know. In this case, the sodium hydroxide. The quantity there was 35.23 milliliters. That's how much it took. That's what I start my calculation with. Now, of course, notice I've changed it to liters, 0.03523 liters, and that's because I'd have to do that anyway, because the very first step, as with any stoichiometry, go to moles. You've got to convert to moles first. All right, I can use the concentration of the sodium hydroxide to do just that. The concentration was 0.250 molar, and remember, capital M stands for moles per liter. So it converts for me liters of the sodium hydroxide to moles of the sodium hydroxide. Capital M, moles per liter. All right, and so I'm going to fill those in. Moles on the top, liters on the bottom. I could have done it the other way, right? But I wanted things to cancel correctly. And I'm starting my calculation with liters of sodium hydroxide. So I put my liters on the bottom, my moles goes on the top. What about the numbers? Well, 0.250 capital M, 0.250 moles per 1 liter. 0.250 moles per 1 liter. I put it into my conversion step. Liters and liters cancels, so my calculation at this point has brought me to moles of sodium hydroxide. Once you get moles of one of those species, you can use the coefficients to go to anything else, any other species at all, in that balanced equation. So I know moles of sodium hydroxide. I'm trying to analyze what? This one. I'm trying to analyze the hydrochloric acid. Alright, so here's my next step. Moles of sodium hydroxide to moles of HCl. According to my balanced equation, it's a 1 here and a 1 here. So that's a pretty simple step. It's a 1 and a 1. But again, if it was a different number out in front, use those different numbers. No big deal. Alright, so moles of sodium hydroxide cancel. I've got moles of hydrochloric acid. Let's see what that actually equals. Pump that through on the calculator. 8.81 times 10 to the minus 3 moles. So that's pretty cool. I'm trying to analyze the HCl down here. I knew it was 50 milliliters, but now, because I've titrated, I figured out how many moles of HCl are actually in that beaker. 8.81 times 10 to the minus 3. Alright, that's almost what they asked me for. They asked me for the concentration of it. Concentration, capital M, which means moles per liter. I just figured out the moles, so there's the top of my fraction. How many liters of the HCl? Well, it was 50 milliliters. That's the same thing as 0.050 liters, right? So there we go. I'm going to do my division. Moles per liter. Pick up the calculator. 0.0176. So I've answered the question. That hydrochloric acid down there, my analyte, what I was trying to figure something out about, after I did my titration, I could tell you it was exactly 0.176 molar. I know the exact concentration of it. And that's really important. Maybe you're titrating, the contents of someone's stomach to see how much acid was in there or something like that. It would be exactly the same kind of a calculation. You do a titration exactly the same way as this. Okay. Now, there is another way that you can go about this. This is true at the end point or the equivalence point of a titration. Now remember we said that the amount reacting equals the amount of the other one, right? The reactant and the analyte, they should equal each other, the moles, or more specifically how much reacts with one reacts with the other. You could use this equation right here, which is going to be true at the end point, or I should say the equivalence point of any titration. The concentration of the one times its volume divided by the coefficient in the balanced reaction. That would equal the other one, concentration times volume divided by the coefficient. So this is essentially taking this type of a calculation and applying it specifically right at the equivalence point and just giving you an equation that you could plug into. Right? Sometimes when you're doing a whole bunch of titrations, it's easier perhaps just to use this one and plug it in directly. Other times when you're trying to think through that reaction and understand the stoichiometry and understand the balance of it, it makes more sense to do it just writing it out as a typical sort of a calculation. But let me show you how to use this. The concentration of the one times the volume divided by its coefficient. So if on this side we put the sodium hydroxide, right, times the volume of the sodium hydroxide divided by 1, because that was in the balanced reaction, it was just a 1. That would equal concentration of the other one times its volume. So concentration of the HCl times its volume divided by its coefficient in the balanced reaction, which again, for this reaction is just a 1. So I've identified what it is. They told me the concentration of the sodium hydroxide, 0.250. They told me the volume, it was 35.23 milliliters. And I got the balanced reaction. I knew that was a 1. HCl, that's what I'm trying to figure out, so I just leave it. That's my unknown. That's my variable. That's my X, if you will. The volume, hey, I know I had 50 milliliters, and again, divided by 1. The only thing to watch out for, if you're using this equation, is that the units are consistent. So if I'm using molarity here, then I'm going to have molarity here. If I'm using milliliters here, I better have milliliters here. All right? As long as they're the same, you're good. And so I have that, right? I've got milliliters on the left, milliliters on the right, molarity on the left here, which means my answer, my variable, will come out also in molarity. All right, so 0.250 times 35.23 divide by 50 over, I get exactly the same answer. Of course I do. So you can do it either way. This way, like I said, is perhaps maybe a little faster if you're doing a bunch of them. This way, you're demonstrating that the knowledge may be more of the reaction of the stoichiometry. And if those coefficients are any different, or if there's some kind of special situation, you can still handle it doing this way. This one's more of a blindly plugging in. So, okay. The second technique for quantitative analysis is called gravimetric. And this one is where you have a reaction that produces some change in state. Now, almost always that means a precipitation. So in other words, I've got two dissolved things. I'm going to react them together. And when I do, I get a solid precipitating out. Right? I could measure exactly how much solid comes out. Right? That is to say, I could dry it off, put it on the scale, and weigh it. Right? And by knowing that, then I should be able to calculate how much of the initial stuff was present. Right? Stoichiometry again. Right? So, example 415, we'll learn about it like that. It says a 0.4550 gram solution of some mixture that contains magnesium sulfate. So it must contain some other stuff. I don't even know what this other stuff is, but magnesium sulfate is part of it. Some other powders, some other metals, I don't know. Right? But magnesium sulfate's in that mixture. That whole mixture weighs 0.4550 grams. All right, they take it and they dissolve that mixture in water, and then they add an excess, a whole bunch of barium nitrate. All right, when they do that, you got a precipitation of barium sulfate, 0.6168. So apparently they took it, they filtered it, they dried it, and they threw it on the scale, and that's how much it weighed, this solid. So notice, I had this dissolved, which is included magnesium sulfate, aqueous, it's dissolved. I added aqueous barium nitrate, so there it is, aqueous. When I did the metathesis reaction, swapping the positive negatives, I got barium sulfate, which is a solid. Look at the solubility rules, all right? It's actually the very, very last one, number 7. Most sulfates are soluble. Barium is an exception, all right? And so it's a solid. And then magnesium nitrate, that nitrate being a -1 makes that soluble. All right, so there's my balanced reaction. How can I figure out the concentration, that is to say the percent of the magnesium in the mixture? All right, we haven't really used this word concentration in this sense because we had this pile of stuff. It was all solid, right? They said it's a solid mixture. Part of it was magnesium sulfate. So I had this pile of powder perhaps, and in there was magnesium sulfate and then a bunch of other stuff. And they're saying, what's the concentration of that magnesium sulfate in that solid? There's no liquid involved. Right? Well, the part divided by the whole, that's concentration. In this case, I might have 100 grams of the whole thing, 30 grams of magnesium sulfate, so I can say 30 divided by 100 times 100 to get a percent, 30%, that kind of an idea. You want to do the part divided by the whole times 100. So in other words, what is the percent? That's what they're really asking. Out of it, how much did the magnesium sulfate weigh? How much did the whole thing weigh? Well, I know that. They told me it up there. Divide times 100, that would be the percent magnesium sulfate. So what I need is to figure out is how many grams of magnesium sulfate was in that pile. If I can get that number, I'll divide it by this and times 100 to get my percent. Can I do it given what they gave me? Well, they told me exactly how many grams of barium sulfate came out. So I'm thinking, yeah, I can convert grams to moles. Once I've got moles of here, I can go back to magnesium sulfate. And then once I'm there, I go back to grams. And that's exactly what I'm after. So let me pull up my notes. I'll show you how that worked. There's all the information right here that we were talking about. And here's my calculation. Oops. There we go, I'm sorry. There's the balanced reaction. Again, solubility rules told me that that was a solid. It will precipitate out. And here's my calculation. I'm starting with grams of barium sulfate, convert to moles. Here's from my balanced equation. Now I've got magnesium sulfate, convert back to grams. 0.3181 grams of magnesium sulfate. So again, I had this initial pile. The whole thing weighed 0.4550. They told me that. I've just figured out in that pile or out of that pile, 0.3181 grams was magnesium sulfate. The other was some, I don't know what the other stuff was. Right? But that's the important thing. I finally figured out the magnesium sulfate. So if I just divide those two times 100, There you go, 69.91%. There's the concentration in that initial mixture that was barium sulfate. All right, so there's gravimetric analysis, trying to figure out how much of something you had by first getting a precipitation reaction and weighing it, and then doing your calculation. All right, number 3, and here's the last one, combustion analysis. Now actually, combustion analysis is another type of gravimetric analysis where I have a change in state, and then I therefore can separate out that one little thing and weigh it or measure it somehow and figure out how much of it was there. Now, combustion analysis is used to analyze some hydrocarbon. You know, hydrocarbons, methane and ethane, or propane gas in a lighter, or butane gas in a barbecue, or octane in gasoline. Right? Those are all hydrocarbons. They're called hydrocarbons because they have hydrogen and carbon. Hydrocarbons, right? Combustion analysis can actually also be used if there's oxygen in there as well. So different alcohols and such, but this book just sticks to the simpler hydrocarbon, and so will I. Right. If you have a hydrocarbon, but I don't know its identity, so I don't know how many carbons and how many hydrogens make up that molecule, so I just leave it as an X and a Y here. And I react with excess oxygen. Right. This is a combustion reaction. We've talked about that before. Remember, a combustion reaction was actually a type of a redox. Right. I always get the same results when I do a combustion reaction on an organic fuel like this. I get carbon dioxide and water. Now, if you look at this, I get CO2, which has one carbon, and all those carbons comes from here. And so maybe there was 3 mixed in here. That means I would have a 3 coefficient out in front. So I actually put an X out. All the hydrogens of the water came from the hydrogens of the hydrocarbon. So if I have Y of them, it'd actually be Y divided by 2 because each one of these has 2 hydrogens. So those coefficients actually are related directly to the subscripts in the molecular formula. All right, that's all true. You don't need to know that to answer the question, but I hope it makes sense to you that, oh yeah, they're going to be related that way. Okay. In a combustion analysis, I'm looking to get this formula, which almost always means the empirical formula. Now, if I know a little bit more, like you saw in a previous chapter, if I know like the molecular weight of the whole thing, then I can get its molecular formula as well. All right. But here, let's just stick to the easier. We'll stick to the empirical formula, and knowing in the back of my mind, if they give me that one last piece of information, I could go that one further step. So how in the world do I get that molecular formula? Example 4.16 will demonstrate this nicely. It says, hey, polyethylene, it's a hydrocarbon polymer used to produce food storage bags and other flexible plastics. All right, we did a combustion analysis, 0.00126 grams of my sample polyethylene. And when they did this combustion, they produced 0.00394 grams of CO2, 0.00161 grams of water. What's the empirical formula of polyethylene? That's what we have to figure out. It's just stoichiometry. That's all it is. Let's set it up. I just copied down the data from the problem. Okay. I'm going to do some stoichiometry here and figure out how many moles of each one I have. All right, I know all of my carbon comes and becomes carbon dioxide. So I'm going to start by looking at the carbon dioxide first. That will tell me how many moles of carbon must have been in that polyethylene sample. All right, 0.0394 grams of carbon. They told me that's how much was produced. I convert that to moles, and then I say, hey, in every one of those CO2s, there's exactly one carbon atom. So 1 to 1. Multiply that out. All right, that many grams of carbon dioxide means there's 8.95 times 10 to the minus 5 moles of carbon. Okay, and remember, all of that carbon came from my hydrocarbon sample. The hydrogen in that sample all became water when I multiplied that out. And so I can do exactly the same kind of a thing. Water was 0.00161 grams when they did this analysis. Convert to moles. And now if I look inside a water molecule, there's 2 hydrogens for every 1 whole water. So there I'm converting to moles of hydrogen next. That equals 1.79 times 10 to the minus 4 moles of hydrogen. Excuse me. Now I've got moles of carbon, moles of hydrogen. That all came from my hydrocarbon sample. That is to say, that all came from the actual molecular formula of my polyethylene in this case. So I can write the formula down, right? This is in terms of moles now, not grams, so I can write carbon that much, hydrogen that much. But we know we don't leave it like that, and you know how to do this next. You divide by the smallest number, in which case, this case, it's the 8.95 times to the minus 5. So you divide through, that's a 1 and a 2. Hey, and they're nice whole numbers, they're not fractions, so there we go. For every 1 carbon, I've got 2 hydrogens. So there's my empirical formula, CH2. Now, polyethylene might actually be C2H4 or C3H6, right? It could be any multiple of that, but we figured out its empirical formula, and that's all they asked me for, 1 carbon and 2 hydrogens. All right, so it's just stoichiometry again, and another way to get at those identities and the actual formulas of whatever I'm trying to analyze.